Welcome everybody to this presentation. Today I am going to present transfer learning with generative adversarial network model for satellite image resolution enhancement, and the paper ID is 22 with the authors Rafiqul Islam, Moshumi Khatun, Sumaya Haidar Poppy, and on behalf of authors I am Rafiqul Islam presenting the paper. And satellite imaging is an essential in many sectors, including remote sensing, environmental monitoring, and urban planning. However, the low resolution of satellite images make retrieving fine-grained feature difficult and limits their usefulness. So, to overcome this resolution, traditionally iterative-based algorithm and deep network-based algorithms are widely used. Iterative algorithms such as interpolation method have limits in producing high quality result and failing to capture complex structure and texture. Deep learning algorithms, on the other hand, have emerged as potential option for overcoming this constraint and achieving significant gains in super resolution performance. However, the key challenges include lack of high quality training data, computational complexity, and determining optical hyperparameters to these problems. Many deep learning based algorithms, such as the generative adversarial network, has also used for super resolution of satellite image. GAN basically include two networks. One is called a generator network and another one is a discriminated network. Generator networks learns to generate realistic high resolution image. On the other hand, discriminated network provide adversarial training to ensure the resulting image are visually creditable. Transfer learning is another popular pre-trained approach in deep learning that can be fine-tuned for resolution enhancement application. The fine-tuned models can extract and exploit the underlying properties peculiar to satellite data by using the learned representation from this model, resulting in increased super resolution performance. There are some preprocessing steps that incorporate the GAN method, such as super resolution GAN, enhanced super resolution GANs, and some few models also propose to enhance resolution and that show better result when used the traditional GAN algorithms. In considering this GAN application, we have developed an efficient approach for enhancing the resolution of satellite image while preserving crucial information and visual characteristics. To accomplish this, we leverage the power of GANs and pre-trained transfer learning model, which have been experimentally validated using a variety of performance. Here, the choice of pre-trained networks, since we don't have much amount of data, that's why we have selected the pre-trained model. And as we know, the super resolution model is an inverse problem that can be formatted by the equation y equal dh plus n. Here x is the original high resolution object and h is the blurring or system matrix, d is the downgrade or sampling matrix, and n is the noise. Super resolution process finds an essential high resolution image h uh, x that optimize the function of the form y, that's mean L2 norm of difference between the original low resolution image and generated low resolution image that also incorporate a regularization term. In our work, we have set training it we have generate a data set from the high resolution satellite image using this observation. That means we have generated or simulated the low resolution image considering the resizing matrix and blur matrix as well as some noise. Generative adversarial networks, as we know, it incorporates numerous layers to upscale and capture complex visual feature as well as the mapping between low resolution and high resolution images. But on the other hand, discriminator uses convolutional layer, activation function, and pooling layer to distinguish between the genuine and produced image, which contributes to the adversarial training process. DenseNet 201. The model has mastered the ability to extract general feature from images such as edge, texture, high-level semantic feature that can use for providing high-resolution image. Here we have there are so many transfer learning models that such as uh, uh, BGG, Inception version 3, ResNet. But one of the major advantage of TransNet 201 transfer learning is can reuse the feature, as well as it can work with small data set. Uh, Also some few features that enhance our model. Since we have only few limited training data sets, that's why we have selected this dense net model. But one can use easily VGG or other model that also produce better result, but that needs large numbers of data sets. That's why in this work we have selected the dense net model. Here is the proposed architecture framework, that means low resolution image. Here we have used some preprocessing step that directly incorporate with our models. For noise and artifacts, we have used bilinear interpolation that did not mention here. And as we already told, the generator that consists of residual block, upsample block, and the discriminator contain the also residual block as well as sigmoid function. Then uh, this GAN and the transfer learning model, uh, the it's called the adversarial loss. That means the some features of transfer learning models, when we combined the loss of transfer learning and the GAN network, that means when we combine these two features, it will automatically improve the overall accuracy of the outputs. That is actually our contribution in this work. That means we have used the preprocessing as well as we have incorporate the GAN loss with the transfer learning model loss. Here is the experimental setup. In our datasets, the original high resolution image content 384 by 384, in total images 200. In satellites, we have categories ocean, forest, and rivers, and some others also. For training ratio is 80%, validation image is 20%, and for augmentation we have incorporated rotating, flipping, and scaling. Here noted that in during the augmentation we have incorporated the nearest neighbor interpolation. For pre-processing, that means when we read the image, then we incorporate the bilinear interpolation to remove the noise and artifacts. For low resolution, we have uh, first considered 200 by 200 image, but after that we have converted it 96 by 96. Here the original resolution image was 200 by 200, but it reduced to 96 by 96. For learning rate 0.002, here we have used the parameter optimization method to select the parameters. But one, if you don't want to use the any algorithm, then you can easily select by using trial and error basis. Here is the sample high resolution and low resolution image. That means in the left side, figure A is the one of the high resolution image, and B is the corresponding low resolution image. Similarly, for another one, C is the high resolution image and D is the low resolution image. Finally, we apply our four algorithm. That means Inception version 3, ResNet, VGG, and our proposed denset. And if we see the image of D, we compare with original high resolution image, that means A, it can easily show the difference. And similarly, when we compare with the Ace with the original image C, then it can also show the difference. This one is the visual difference between the proposed algorithm with others algorithm. Similar for qualitative measurements, that means once cannot understand, or when we can not find the difference between the original output image, then one can easily use the peak signal to noise ratio and structural similarity index measure. More the PSNR value, the better the quality of the image. Similarly, the structural similarity index measure, more it's near close to the one, that means it produce good result. Here if we see the proposed algorithm, the PSNR is 36.28 decibel, whereas the SSIM is 0.8304. In this result, we have used the DenseNet 201 that easily extract general feature from the image. And as we know, satellite image has edges, texture, and high-level semantic feature that improve the overall accuracy than others. Also, it's highly parameter efficient and facilitate the gradient flow during backpropagation. One more thing is it can it works with small data sets. This is the advantage of testnet 201 model. Finally, if we conclude the model, we can show that the use of interpolation in the pre-processing stage to remove noise and artifacts that enhance the overall accuracy. Also, the presented paper show an acceptable accuracy in terms of super resolutions. In future, we can hyper parameter we can tune the hyper parameters on all others model can be fine tuned, and large image data set can be used, and try to improve the accuracy all other algorithm. At the end, we can combine multi-scale model to combine these laws with the generative adversarial network for further investigation. And this is the reference. Finally, we thanks Department of Computer Science of Engineering of Dhaka University of Engineering and Technology. And that's all. Thank you. If you have any question, you can ask me. Thank you.